This paper presents an outdoor vision-only localization framework based on an omnidirectional camera targeted at low-speed, resource-constrained autonomous vehicles operating in urban pedestrian environments, such as footpaths and pavements. Typical examples of target devices range from personal mobility devices, or PMDs, such as mobility scooters and powered wheelchairs, to applications such as delivery robots. The proposed framework leverages the use of CNN-based high-level semantic observations with an EKF-based backend in order to provide a low-cost, resource-efficient vision-only localization solution suited for such devices. An information theoretic strategy is utilized to decide the best viewpoint to serve as the input to the CNN instead of the full 360 coverage offered by an omnidirectional camera in order to leverage the advantage of having a higher field of view without compromising on performance. Before presenting the details of this framework, we will first discuss the state of the art with respect to vision-only localization. Now, localization remains one of the most fundamental tasks for an autonomous vehicle, since an accurate position estimate is instrumental in safe and robust navigation. GPS in dense urban environments is unreliable for this because of multipath errors and ionospheric interference. So most fast-moving self-driving vehicles use a suite of sensors ranging from LiDARs to vision sensors coupled with dense 3D point cloud maps of the environment. But this approach takes a lot of resources and requires expensive sensors, which makes them unsuitable for resource-constrained applications such as PMDs. In fact, the limited operating conditions of these devices, such as lower speeds, more defined paths, means we should be able to carry out localization with far less resources. Thus, our proposed system uses a vision-only localization approach coupled with a very sparse 2D map. Traditional state-of-the-art vision-only navigation can broadly be looked at in two categories: feature-based techniques that use low-level handcrafted features for motion estimation, such as OrbSlam2, RTabMap, WINS, and Chimera, and appearance-based techniques that use direct pixel intensities for motion estimation, such as LSD-SLAM and DSO. However, making a pre-built map using these techniques that can be reused over long time frames becomes difficult due to appearance changes and dynamic objects found in urban outdoor environments. So, these approaches generally rely on SLAM or plain visual odometry, which is computationally expensive at scale and prone to drift, needing robust loop closures to fix, which isn't always guaranteed. In contrast with these traditional vision-based approaches, the proposed work utilizes persistent, high-level CNN-based semantic features found in typical urban environments. This includes the following types of observations. Number one, environmental landmarks, such as trees, parking meters, lampposts, extracted using the YOLO object detection framework. And number two, ground surface boundaries corresponding to curbs, pavement edges, manhole covers, extracted using the HED, edge detection network. These observations are then fused with odometry data using an EKF-based backend. Utilizing these high-level features as opposed to low-level handcrafted features enables us to carry out localization on a sparse, pre-built 2D map. The map consists of 2D locations of landmarks and a vector distance transform representation of the ground surface boundaries. Utilizing a pre-built map overcomes the inherent drift and computational load associated with having to carry out SLAM at large scales, and the need for corrective loop closure, which is incompatible with efficiently traversing from point A to B. This paper is an extension of our previous work, which highlights this overall approach. The key extensions and contributions of this paper are as follows. Number one, the use of an omnidirectional camera as the primary sensor for CNN-based perception of environmental landmarks. And number two, an information gain-based active vision paradigm for perspective viewpoint selection to improve the efficacy and functionality of the proposed framework. The main motivation for these contributions are to address a key limitation to the robustness of our previous work due to the sparse nature of the bearing-only landmark observations. This has been achieved by increasing the field of view while balancing the computational overhead this brings. The CNN-based object detection framework YOLO was utilized to extract the persistent landmark features as it provides exceptional accuracy and real-time performance. However, YOLO did not perform well on the raw dual fisheye images obtained from an omnidirectional camera, even when trained using similar dual fisheye images for the following reasons. Number one, the non-consistent distortion in the fisheye images affecting the accuracy. And number two, the high resolution in the dual fisheye images affecting the detection rate as well as the accuracy, since landmarks were too small relative to the rest of the image. This issue was further exacerbated by the unavailability of a CNN framework that works with fisheye images that offers the same accuracy and real-time performance that Yola does. Thus, since our landmark detection approach performs far better with undistorted perspective images, the following projection pipeline was adopted. Dual fisheye omnidirectional cameras consist of two fisheye lenses that each cover a field of view of 180 degrees horizontally and vertically. Consider figure A. A single fisheye camera can be modeled based on a spherical projection. Here, a 3D point P is projected onto a sphere of radius equal to the focal length of the camera. This is then projected onto a circular image plane, which provides the typical raw, distorted circular fisheye camera output. In the case of two fisheye lenses providing 360-degree coverage, this creates a dual fisheye image as seen in figure B. This is the raw output of a typical omnidirectional camera. As seen in figure C, reprojecting the dual fisheye image onto a spherical projection with radius 1 gives an image that behaves as a scaled-down version of the 3D spatial information of the real world while preserving the bearings. Sections of this unit sphere can then be projected from the center of the sphere onto an image plane using a standard pinhole camera model to obtain undistorted perspective images as seen in figure D. This projection pipeline can be utilized to undistort any section of the dual fisheye image and obtain a perspective image. Utilizing the undistorted perspective images resulted in a detection performance comparative to using a conventional perspective camera. However, for real-time performance on the current hardware platform, only a projected perspective window representing a 416 by 416 pixel image with a horizontal and vertical field of view of 60 degrees could be processed in a single iteration. To mitigate this issue, an active vision strategy was adopted. The key to this strategy was understanding that, considering the sparse nature of landmarks in a typical urban scene, consistent tracking of important landmarks over a long time period is more important than observing the whole surroundings at a given moment. Thus, an active vision approach was developed to select the best viewpoint to undistort out of 4 possible fixed viewpoints within the unit sphere projection. The viewpoint selection process is carried out as follows. At each iteration of the EKF, the predicted pose obtained from the motion model is utilized to generate a set of predicted observations using the landmark map for each potential viewpoint. A hypothetical update step for each viewpoint is then carried out to obtain 4 possible predicted covariances for each viewpoint. In order to quantify the information related to each viewpoint, the trace of these covariance matrices, which provides a strong measure of the pose uncertainty, is calculated. A metric delta PVP is then calculated for each viewpoint, which captures the potential drop in uncertainty. This provides a straightforward scoring system for each viewpoint. The viewpoint that provides the most information will correspond to the higher delta PVP value, or the biggest drop in covariance. This viewpoint will be selected and projected onto a perspective image, which will then be sent for CNN-based landmark detection. To deal with scenarios where landmarks may be occluded, the system uses a heuristic to switch to the viewpoint with a second higher score when no detections are reported consistently from the selected best viewpoint. Once the best viewpoint is selected based on the predicted pose, and YOLO extracts the necessary landmark observations, the bearings to these detections are fused with ground surface boundary observations using an EKF framework in order to estimate the pose and associated covariance. This follows the standard formulation of the EKF. A detailed explanation can be found in our publications. This framework was implemented on a modified off-the-shelf mobility scooter. A low-cost, consumer-grade Ricoh Theta S omnidirectional camera is used as the primary vision-based sensor for landmark detection. A rear-mounted tilted rear-sense D435 sensor is used to obtain ground surface observations. An RTK GPS and Hokkyo laser is also mounted purely for evaluation purposes and map building. The primary computing unit is an NVIDIA Jetson Xavier with an Intel upsquared board acting as a secondary unit. In order to demonstrate the capabilities of the proposed framework in a dynamic, real-world urban setting, a set of experiments were carried out in a roughly 8,000 square meter area in Glebe, Sydney, Australia. Ground truth data for this experiment was obtained using the RTK GPS unit. However, RTK GPS provides centimeter level accuracy only under the condition that a clear skyline is available, free of any multipath errors. Thus, continuous fixed RTK GPS measurements were hard to come by due to the buildings and trees obstructing the skyline. Hence, quantitative error calculations were carried out based on sporadic ground truth data available whenever RTK fixed readings were obtained, shown here in red. 3 state-of-the-art vision-based SLAM systems, OBSLAM2, WINS Fusion, and RTAP, were used to establish a comparison. The path taken by the scooter does not provide any opportunity for loop closure, which causes these SLAM-based state-of-the-art systems to eventually drift. The following video indicates the full projection framework in action. First, the raw dual fisheye images are obtained from the camera. Then, a unit sphere projection is carried out. Based on the active vision strategy described earlier, a viewpoint within the sphere is selected and undistorted into a perspective image. The final row of images indicate the output of the CNN-based landmark detection and ground surface extraction. The 2D map of the environmental landmarks and vector distance transform representation of ground surface boundaries were constructed based on known vehicle poses roughly 6 months prior to the data collected for localization. Results also indicate that the accuracy of the proposed active vision strategy, where a single perspective image is processed at a time, is comparable to that of feeding all 4 perspective images in an unconstrained manner without considering processing limitations. This shows that in this particular environment at least, that the active vision strategy is successful in taking full advantage of the available field of view while balancing performance accuracy with processing limitations. This is perhaps because the landmarks in this particular environment are sparse enough that only choosing a particular viewpoint instead of processing the whole image has a negligible effect on accuracy. We concede that this might not be the case in a different environment with a dense number of landmarks spread evenly within a 360-degree view, in which case we posit that processing the entire 360 field of view, although impossible in real time on the current platform, may yield better results. To further improve our framework, we are currently investigating the possibility of using cellular-assisted GPS, which we have found to be fairly more accurate than regular GPS within urban environments. We are also looking into more comprehensive map building and maintenance strategies, which also includes incorporating uncertainty information into the sparse maps currently being used, which can tackle the possibility of large-scale infrastructure changes that can alter the map. In summary, utilizing CNN-based environmental landmark observations and ground surface observations enables our framework to carry out vision-only localization on a pre-built 2D map that is suitable for resource-constrained applications such as PMDs. Utilizing an omnidirectional camera for this purpose improves the robustness of the framework by providing a higher field of view, and the implemented active vision paradigm ensures that this does not compromise on the overall computational limitations of the practical hardware system. Thank you.